In this video, we discussed the second law of thermodynamics. We already mentioned several versions of the second law of thermodynamics. For example, when discussing heat engines, we mentioned that it is impossible for any system to undergo a process in which it absorbs heat from a reservoir at a single temperature and converts the heat completely into mechanical work, with the system ending in the same state in which it began. Then, when considering the Carnot cycle, we have seen that another version of the second law is that no engine can be more efficient than a Carnot cycle. And when discussing refrigerators, we mentioned one more version, which is that it is impossible for any process to have as its sole result the transfer of heat from a cooler to a hotter body. And finally, when discussing entropy, we mentioned that no process is possible in which the total entropy decreases when all systems taking part in the process are included. So in this video, we will see that these statements are equivalent. So let's imagine a heat engine that does not need a cold reservoir. So the hot reservoir is losing heat, so the entropy change of the hot reservoir is negative. Then the engine runs in a cycle, so its initial state is the same as its final state, and since the entropy is a state function, then delta S is 0. So if there is no cold reservoir, the total entropy change when adding the engine and the hot reservoir is negative. And this is impossible according to the second law of thermodynamics. So the statement that no process is possible in which the total entropy decreases when all systems taking part in the process are included is equivalent to the statement that it is impossible for any system to undergo a process in which it absorbs heat from a reservoir at a single temperature and converts the heat completely into mechanical work, with the system ending in the same state in which it began. Now, let's imagine a refrigerator that does not need work. If that was possible, then we could combine it with a heat engine. All the heat that is rejected by the heat engine to the cold reservoir could be transferred back to the hot reservoir using the workless refrigerator. And so this combination would be an engine that takes heat from a hot reservoir and converts it into work without rejecting heat to a cold reservoir. And we just saw that this is impossible according to the second law of thermodynamics. So the statement that it is impossible for any process to have as its sole result the transfer of heat from a cooler to a hotter body is equivalent to the other two statements. Now finally, let's consider the thermal efficiency of a heat engine. We have seen that the efficiency is equal to 1 minus absolute value of QC over QH. Now, we assume that the temperature of the hot reservoir does not change, right? It's a reservoir, it's big, so its temperature doesn't change. So for the hot reservoir, the entropy change can be calculated as QH over T hot. And for the cold reservoir, it is QC over T cold. Now, this gives us the relation for the efficiency as 1 minus T cold delta S cold over T hot delta S hot. Now, the engine runs in a cycle, so for the engine, delta S is equal to 0. So the total entropy change when we consider the reservoir hot and cold and the engine, the total entropy change is delta S hot plus delta S cold. Now, according to the second law, the entropy change, the total entropy change cannot decrease, right? So it is either not changing or it is increasing. So if it is not changing, then delta S is equal to 0. This means that delta S cold is equal to minus delta S hot. And so what does this mean? That means the cold reservoir receives heat, its entropy increases, but the hot reservoir is losing heat and its entropy decreases. And this relation tells you that the amount of entropy increase for the cold reservoir is equal to the amount of entropy loss for the hot reservoir. Now, combine this with the relation of efficiency, and you can simplify by the absolute value of delta S. And so the efficiency the efficiency is equal to 1 minus T cold over T hot. And if you remember, this is the same value as we got for the Carnot efficiency. Now, if the total entropy increases, then delta S is positive, and so delta S cold is larger than minus delta S hot. And so that means the entropy of the cold reservoir increases more than the entropy loss of the hot reservoir. And so in that case, you see that the efficiency will be smaller than the Carnot efficiency. And so you see that saying that no process is possible in which the total entropy decreases when all systems taking part in the process are included is equivalent to saying that no engine can be more efficient than a Carnot engine. And this is equivalent to the other statements that we already discussed.